Good day. Welcome. This is Peter again. Welcome to the shack, or the lab as I sometimes call it, but essentially it's the same place. Today I'm going to introduce you to the ePoynt. Now, the ePoynt is an antenna with a difference. It's an antenna that's been developed by Poynting, which has a cavity at the back, which I'm going to show you, where you can fit your own router. Now, the rationale behind that is that the radio frequency cables or RF cables that runs from the antenna down to the router often becomes very long, sometimes tens of meters. Now, this radio frequency cable introduces attenuation. That attenuation is sometimes more than the actual gain of the antenna, almost negating the effect of having an outside antenna. Now, of course, we're talking about outside antennas as far as the ePoynt is concerned. So this is going to be a mini unboxing. So I'm going to show you what the unit looks like. This is, in this case, is the ePoynt-2. The ePoynt-2 is a directional antenna. The specs is on our website. And when you open the box, this is what you're going to find. This is the unit, and this is the installation kit. We'll have a look at the installation kit in a moment. Let me first show you our ePoynt-2 in this instance. Now, I've got to be careful because I've actually taken it apart already, so I can show you what it looks like inside. Right, so if we open the back, this is the back cover. I'm going to take it off, put it over here. This is the cavity, so to speak. Beneath the cover, a waterproof cover, where you can install your router. It has various connection points where you can attach the router, and then we have the main cross-polarized antenna for what we call cell 1, the main and the diversity, and then the second cellular 2, where you've got a main and a diversity connection. Therefore, routers like the Teltonica RU2X14 that has a main cell and a second cell, 2 SIM cards, can be accommodated in this specific unit. You also have the facility. There's a vertical and a horizontal Wi-Fi antenna included in here. So when you have this installed in an area where you also want to create an access point from the router, you have the antennas to actually do that. So this is the back. This is the backing plate. In the backing plate, you've got a facility to bring the Ethernet cable, because obviously an Ethernet cable is going to come into the router, and we're going to show you that. You have the facility for a pass-through USB. You also have RF cable throughput for should you want to install a GPS receiver antenna. You've got an RF exit point and a second RF exit point over here. A grounding pin, which I did not discuss earlier. Then, of course, on the other side, if I am careful here, I'm going to open the front for you. And in the front, you see our patented directional antenna, the same as what we have in the XPOL-2. So this is, in fact, the XPOL-2, now in the ePoynt-2. Right, so let's have a look at the installation kit. When you open the installation kit, what you will find inside is, first of all, a 5-meter Ethernet cable, Cat5e. You're also going to find an installation guide. Now, the installation guide has everything you need, from the tools that you require to a step-to-step manual on how to install. Everything is in here. Also, what you will find, I'm going to put this down over here. Also, you will find is some pipe clamps if you're going to install this. And let me just show you the backing plate. The backing plate has this rounded area plus position for a pole mount. And later on, I'm going to show you an actual pole mount of both the XPOL the ePoynt-1, which is the omnidirectional unit, and then also the ePoynt-2, which is this directional unit. And we're going to have a look, have a proper teardown, and see how it performs with my eNote B that's close to my residence over here. So apart from the pipe clamps, we have the wall plugs. So if you're going to do a wall installation, here's the wall plugs. And then also here is the compression gland that's going to be connected to, if this is the backing plate, what you're going to do is you're going to feed the Ethernet Cat5 cable, Cat5e, through here, and you are going to put the compression gland in here. You can also make use of a compression gland that is a split compression gland to close up the area around the cable. Right. The last unit and we're going to actually show that the last in the installation kit here are the window suckers, as we call them. And you will see later on, I'm going to install our ePoynt-1, which is going to be the first test. Later on, I will show you the test of that same unit on a installation pole, and then I'm also going to install for you the ePoynt-2 on a pole. The suckers works extremely well, and for people that are in residential areas, urban areas, where it's extremely difficult due to a high-rise building, an apartment, a condominium, in a high-rise building where you don't have access to the outside wall to put a mounting pole or even mount it against the wall. These window suckers works extremely well, and you'll see when I install it on a window that I have outside my lab here. So without further ado, let's have a look at the unit itself. Obviously, with the router placed inside of the unit, the cover obviously on top as such, the access to the SIM cards is restricted in terms of the fact that one actually needs to remove the cover to get to the SIM tray. So in the case of this is a Teltonika RUT240, the Teltonika RUT240. There you can see the SIM slot. Now, if this unit, of course, is installed inside, one would need to remove the back cover in order to change SIMs. So what we've done is you will have a SIM extender. The SIM extender slides into the SIM card slot and makes connection with the pin slots that the SIM would normally make contact with, and that then extends to a SIM extender that protrudes from the outside. You just knock out, like I mentioned earlier, you knock out those knockout plates, and the SIM extender gets installed, and now one can actually have a weatherproof SIM socket where you can actually replace the SIM without having to take off the outside cover. And what we're going to do is we're now going to attach the router in the back cavity of the ePoynt-1. Right, so what we have is we have the faceplate, so to speak. Again, just to show you where the knockout plates are for the SIM seals. This is where the SIM extenders go in. Right. So what we have is we have this compression gland, and we have our Ethernet cable. So this is a little bit tricky. Of course, remember to put the compression part of the compression gland through first. And then this gets a little bit tricky. You've just got to feed it through the fingers here on the compression gland. But once it's through, it's quite easy. and then of course the compression part of it gets screwed in. Don't screw it in all the way, because what we're going to do is we're going to first feed the cable through here, through the slot, and then we are going to finish installing first the bottom part of the compression line. It has a very tight seal. And then once that is tight, we proceed with the bottom part of the compression line and screw it right down. Now there is a spanner in the kit as well, if you really need to tighten it further. There we go. Right, so with the Tatonica RUT240, I don't actually have the little lips for bolting it down into the receptacle slots in the back of the ePoynt-1. So what I've done is I've got some double-sided tape for now. So since this is a temporary installation, I'm just going to fix it like that. Please, of course, make sure that you follow the proper installation procedures. We are working on a cradle that will be useful to install your router of choice in the back cavity over here. So what I'm going to do is I'm going to place it such that I've got space for the RF cables. The RF cables, of course, are going to go there, as you can see, and the Ethernet cable is going to plug into the LAN port over here. So I've just got to make sure that I've got enough space for the cables, and then stick it down like that. That is typically where you will install it as well when you've got the proper these are the little bolts. So now I'm going to proceed in installing the RF cables. Now, as you can see, and I'm going to quickly show you this, I have a measuring tape here, and you can see that these cables are 350 millimeters long. There you can see. So that is a huge advantage as far as minimizing the losses on the RF cables are concerned. So I'm going to install these two cables. Now the primary, the XPOL cross polarized antennas, is cell 1 over here. So I'm bolting these down, and then it gets attached to the main antenna, and this one will go to auxiliary or the space diverse. If you have an SMA torque wrench, that is a good idea, but typically just a little spanner will do. So just to show you, that's how the cables will go. Right, so far so good. So all that remains now is to install the back cover. Just make sure that the slot lines up at the bottom here where the faceplate is. Right, and then we're going to bolt it down. Right, so there we are. The next step is installing it against the window. The printout from Cellmapper, and you'll see the street view of the area where we are. The circle is where my residence is, and then the arrow points to where the tower is. So the second one that's going to come up now is the satellite view. So you'll see this is a semi-urban area, urban. We live in a security complex, and again the circle and is where the house is, the residence is, and it points the arrow points to where the tower is. So you'll see it's 350 meters from here. However, when I show you the Google Earth, you'll see the measurement. You'll see the heading. It's at 195 degrees, which is what I'm going to use when, incidentally, when in a following video, I'm going to use the directional antenna, and that, of course, is important for me to know what the heading is. Um, but you'll see the profile. When you look at the profile down there, you'll see that from here, I've got a bit of a hill, and that hill is quite densely populated with urban housing as well as quite a bit of vegetation. And that would be the reason why later on you'll see the signal that I'm getting is quite challenged in terms of its level. And this is quite a noisy environment. It's an urban area. There's a lot of noise, a lot of radio systems around here, and you eventually see when I look at signal to interference and noise that it is significant. But you will see the improvement that an external antenna makes vis-a-vis an internal antenna. So the next one I'm showing you is the actual residence from the satellite view, and just to give you an indication of what the direction of the tower is, you'll see that we right down by a river, and then I've circled the area up on the balcony where the window is and where the mast that you will eventually see that I'm also going to use to install antennas on is. So that is the locale. I'm going to show you now how I'm going to install the ePoynt-1. That's, remember, the omnidirectional antenna against the window over here. So, so here I have the unit. You can see here that the window suckers are installed, and I'm going to just quickly show you how I'm going to install it against the window over here. Now, this cable, remember the cable that we've shown previously installed, this particular cable is going inside. Inside I have an Ethernet switch with PoE, in other words, power over Ethernet capabilities, and that is currently driving our ePoynt-1, and of course the router, the RUT, Teltonica RUT 240 that I've installed as you've seen previously on the antenna. So right, without further ado, I'm going to stick it up against the window here. This is the balcony, the lab is right here, and this is the window where I'm going to install the unit. So you can see all I do is I'm just pushing it up against the window. I'm just pressing hard on it so that it pushes out the air and creates a vacuum in the window suckers. These are silicon window suckers, and we've actually had some of these units at our offices stuck on a window for more than a year now. In fact, it's probably about a year and a half, if I remember correctly. There we go. This particular cable, as I've said, is going to our router with the power over Ethernet. That's powering our router inside here. This particular cable, this gray cable, you're going to see this cable downstairs. This is connected to the Ethernet switch. From the previous insert, I spoke about the position of the residence, and I thought I'd give you a street view of the tower that I'm working to. So when you look at the picture on screen now, I'm literally looking at a heading of 195, as you saw, 195 degrees, which which of course is 15 degrees towards the west of due south. So just as a point of interest, that's the tower that I'm working to. That's running on LTE bands 1 and bands 3. And we'll see when we look at the router which bands the system will choose. I'm now downstairs from the lab. The lab is upstairs. And what we're going to do here is we're going to test internal antennas versus the ePoynt, of course, with the external antennas. With it. So what you're going to see on screen is I'm going to show you a speed test. And remembering that this contract is a 20 megabit per second contract that I've got here. So you'll see the performance of the 20 meg full on from the ePoynt upstairs versus the connection from this. So first of all, I'm going to show you the RSRQ, RSRP, and the signal to interference and noise ratio of the ePoynt, which is obviously upstairs receiving a better signal, versus what this signal is. So first, I'm showing you an insert of the upstairs, the ePoynt, and you'll see that our signal strength, RSSI, was 67 dBm. The RSRP came in at 96 dBm, RSRQ at minus 11 dB, and the signal to interference and noise came in at 4.9 dB. So I'm going to actually discuss the comparison between the two internal antennas and the external antenna, of course, the ePoynt-1 up on the window here. And the next one I'm going to discuss is going to be the internal antennas. And then last but not least, we're going to summarize and we're going to look at the two relative to one another. To disconnect this cable, and I'm going to connect this guy over here. Right. So let's just get the connection going. Right, and what I'm doing right now is I've connected to the web interface of this unit so that I can show you the RSRQ, RSRP, and the signal to interference and noise ratio of this guy. Signal strength came in at minus 77 dBm, but the reference signal receive power came in at 106 dBm. The RSRP came in at minus 106 dBm, as I've said earlier. The RSRQ at minus 12 dB, and then the signal to interference and noise came in at 2.3 dB. Now, this is quite a noisy environment. This is not a particularly good signal to interference and noise per se, but at least the improvement, we can see the improvement in light of the fact that we have a noisy environment was quite good, and we'll discuss the comparison between the two just now. There's just a few notes that I want to make, and that is you'll see that I've been at the right bottom side, you'll see a refresh button just to let you know. I made sure that I refreshed the actual results from the Teltonica web interface very often. And then as far as the speed test is concerned, the numbers that you see on the speed test is actually a number of consecutive calls that I made on the speed test. So the speed test results, kind of the average, so that because of an active tower, one needs to be conscious of the fact that you need to take multiple measurements in order to find a average. And that is just to say that the improvement that I'm going to show you as far as the antenna is concerned is the average over a number of measurements that I've done. So our comparison is next. Right, so here we are at the comparison. I'm going to flash up on screen now the actual results compared with one another. At the top left hand, you'll see a small version of the results that I've shown you earlier of the ePoynt, the cross-polarized omnidirectional antenna. And then at the top right, you'll see the download upload improvement. Now you'll see that the upload improvement was an excellent 89.7%, and the download was 39.53, which is close to 40%. Now, this is quite an active tower, and there's probably a lot of downloads. In other words, the congestion in the downlink is probably quite significant, and that's would be my explanation why there's such a difference between the upload and the download. But nevertheless, a very significant improvement. Now, if we look at the radio frequency improvement, you'll see that the reference signal receive power improved by 10 dB. Now, that's significant. In practice, that is one of the things that you can look at that'll make a huge difference in terms, and we can see that there's a difference. Now, the reference signal receive quality only improved by a dB. Now, that's a more complex measurement because there's a formula involved that takes into account the number of reference blocks, the bandwidth that's being used, etc., etc. And you can see that the signal to interference and noise ratio at the bottom there has improved by 2.6 dB. That's also significant. Now, just a note, in order to understand RSRQ, we need to look at signal to noise ratio in general. Let's start. That is, if that's a sine wave, prior to LTE, we used a system, and it's actually still being used, but obviously in a modified way, which I will show you now. This was known as, or is known as, QAM, quadrature amplitude modulation. And in very simple terms, we code in the amplitude in the quadratures of each one of the different phases of the sine wave. We actually create what is known as a vector diagram. So that would be the representation of a number of bits. In this case, this would be 16 QAM. And the way we get to 16 QAM is that we've got four bits represented in each one of these quadratures. So it starts off at 0, 0, 0, 1, 1, 0, etc. Right. Now, in comes noise. And noise would typically be something that's modulated on top of the carrier envelope. And what we would typically do is look at the size of the noise. That's the noise. We would look at the size of the signal and calculate signal to noise ratio. Now, what was the importance of noise? Why is noise such a problem? You can see here, if this noise were to impact, if it was large enough, it would actually start impacting the modulated signal and cause us to lose bits. And just now I'm going to talk to you about Datacomms 101, what happens when you lose bits in a data frame. Now, with LTE, things are slightly different. What they are doing in LTE is to create not just a single carrier like we have over here, but if this is the frequency domain, this is the amplitude domain, and if you can imagine the time domain going down like that, we use a system known as OFDMA, which stands for Orthogonal Frequency Division Multiple Access. Now, first of all, a number of carriers are created. And then the orthogonal part is that we realized that we could have these overlap, and since we have a look at the time domain and create different time slots, we could get these to not interfere with one another and overlap in the time domain. So we have these time slots. Now, you can see that in order to look at signal to noise, we now have a dilemma because there's multiple carriers, different subcarriers here, and they use two systems. The first system is just known as FDMA, Frequency Division Multiple Access, and TDMA, which is time division, multiple access, which is the time domain. So they had to make a plan. The plan they made was to create different blocks that are known as resource blocks, reference signal resource blocks, and we would measure the power in those blocks. And since they're always located in the same spot, in other words, in the same subcarrier, in the same time slot, we could create a reference signal. In other words, everything would be referenced to that reference signal receive power. So they had to devise a formula to now look at the total noise that is in the channel. So in a 20 megahertz channel, they defined that in 100 resource blocks, they would measure the total power known as the RSSI, or a received signal strength indicator. And this would actually contain the interference plus the noise, and we would then take that number and take it as a portion of that number and then create something which we call reference signal receive quality. So how is traditional signal to noise ratio calculated? So signal to noise ratio traditionally was 10 times the log of the power in the signal over the power in the noise. So let's say we have a 1 watt system. So this is 1 watt, the signal. So that's the signal. And if you remember, we measured the noise over here. So if that's the noise, and let's make this 10 milliwatt of noise that we measure. So if you calculate this out, that's 1 over 10 times. Well, this then comes out as 100. And as every good schoolboy knows, log of 100 is 2 times 10. Remember, we're talking about SNR all the time. So SNR, signal to noise ratio, is 20, and now we're in dB. So if we looked at this signal, this would be 20 dBs, and you can see, because I'm measuring the power in the signal over the power in the noise, this is a positive number, and you'll see that with signal to interference and noise, that's the same. Now, what they do in LTE, 4G, 5G is, instead of just taking the noise, they take the noise and the interference signal in those resource blocks, and they calculate a number very much along the same line, but we now include interference in here as well. And again, we come to a positive number, and you'll see the greater the positive number is, the better the signal to noise ratio. Now, remember that this now happens in all of those subcarriers, and it is measured in the reference blocks as shown before. Now, RSRQ is totally different. So with reference signal receive quality, they take what is known as reference elements in a resource block, and they take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's hope that's equally spaced. So there's 12 subcarriers, and in a reference, there's reference elements in a resource block, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 subcarriers, and there's a block there,
and a block there that is defined as the reference signal. Now, the other blocks are data blocks. So each one of these will carry data. And let's say we have 1 watt of transmit power. So the maximum power in this block and in this block will be 1/12 of the power, in this case 1 watt. So 1 over 12 of 1 watt is 0.33. Now, reference signal receive quality is defined as 10 times the log of RSRP over RSSI. Now remember that RSSI is the total power in this entire block. That's before we get to noise. So now you can see, now we're getting to a fractional number because obviously the receive power, the reference signal receive power is going to be less than the RSSI, the signal's strength indicator. So 1 watt, we've already seen 0.833 over here, 0.0833 over here. Now, this is the average of the power. So, again, as 8.33 times 2 divided by 2 blocks is again obviously 0.0833. And then if we do the calculation, the total power with no loading in here is obviously that added, and that's 1.667 if you calculated it correctly. And this comes out as 8.5. So here we go. RSRQ equals 10 times the log of 0.5. And as we know, that becomes 0.3. And it's minus, of course, 10 times minus 0.3 is minus 3, of course. So to recap on your RSRQ measurement, remember RSRQ, we look at the reference signal in the reference element block with no loading. There's only the 2 signals, that's 1/12 of 1 watt, and that is 0.0833 watt, no loading, and it comes to 0.5. So what we do is we take 0.0833, we take the total power, which of course is these 2 added. This comes to a half. The half, 10 times the log of a half is minus 0.30103 to be exact, and minus 3 times 10, of course. So this becomes minus 3.0103 to be exact dB. This is the best value. In other words, no loading. Right, so now we need to look at the full loading. Obviously, when this is fully loaded, we've said this is in a 1 watt system. So now our calculation becomes 10 times the log of 0.0833 divided by 1 watt is, of course, the 10 times the log of 0.0833, and that becomes 10 times, when you calculate this out, you will see this is 1.07935 to be exact, and that of course is 10.79, let's make it 4 dB with fully loaded by the actual carrier power, that is. Right. So obviously, as interference and noise gets loaded onto this 1 watt, this fraction will become smaller and smaller. This number, minus 10,794 in this case, will start going down, and anything between minus 10 dB to minus 15 dB is regarded as still good. As we start going between minus 15 dB to minus 20 dB, we're on the cell edge, or mid cell at least. And then anything that becomes smaller than minus 20 dB, RSRQ, starts becoming problematic. Why is noise creating such a problem in terms of throughput? In order to have a look at that, we need to go back to basic datacomms and datacomms 101, and we look at something known as the Ethernet frame. An Ethernet frame consists of what we call a preamble, and that is 7 bytes long. Then there's a 1 byte start of field delimiter. This tells the system this is where my Ethernet frame, which is at the data link layer, by the way, also known as the media access control layer, or layer 2. Layer 1 is the physical layer, and that is the actual RF signal, the radio frequency signal. Encoded in that is the Ethernet frame. So this is the destination address, incidentally 6 bytes long. This is the source address, 6 bytes long. Then we used to have a type field, which was used to be 2 bytes long. Mostly now it has become a 4 byte with a VLAN address included. Then we have the payload. Now the payload is where the actual data gets carried, and that is 46 bytes to 1500 bytes long. Then we have a very important 4 byte field known as the frame check sequence. The frame check sequence is a number that gets calculated through an algorithm known as a CRC, cyclic redundancy check. It actually checks every bit on this frame to where to just before the frame check sequence, and that calculates and stamps it to tell the receiving system there should be so many bits. When the receiver receives it first looks at this number, puts it through the algorithm, and see whether it gets the same number. If it doesn't get the same number, it discards the frame. At the data link layer, it simply discards the frame. From there, we actually have the IP layer, known as layer 3. This is where the IP address lives. So we'll just draw it like that for simplicity. And there's a header, and in the header, there's the IP address, etc. This frame gets mapped, the data link frame gets mapped into the IP frame, and the IP frame gets mapped into the fourth layer, known as the TCP layer, that stands for Transmission Control Protocol. It has a header. I'm not going to go into the detail of that. Suffice to say that in each payload, it carries the IP layer. So each one is carried in the next layer up. What is very important in the transmission control protocol layer is we have something which forms part of what we call segmentation and reassembly. Now, segmentation is, let's say you have a spreadsheet. The whole of the spreadsheet data cannot be sent at once. So the spreadsheet gets chopped up into little bits, segmented, and then reassembled on the other side. And that reassembly takes place to the upper layers, and it takes place in the transmission control protocol layer. When the transmission controller protocol layer looks at the sequences of packets coming from the data link layer, once one has been discarded, it will find that there's a sequence missing and it needs to ask for a retransmission. That retransmission is asked from the transmitting station. Now, if the receiver is receiving a lot of noise, it becomes deaf to the acknowledgements coming in. And that is why sometimes we find that the uplink has a transmission problem, simply because the receiver, in other words, let's say my residence over here, and you're going to see it in the next video where I'm putting the ePoynt up on the mast. There's a lot more noise. It becomes deaf, and it's not listening to the requests for retransmission, or shall I rather say, I'm sending a packet up. That packet gets discarded because of noise, and a request for retransmission is sent back to me. But because I've become deaf, the radio here, because of the interference of noise, I don't get that request for retransmission. And I keep on sending, it keeps on getting discarded. The main result is the actual throughput up to the on the uplink gets bad, simply because of a bad signal to noise ratio on my receiver side. So I hope that makes it clear as to why in the next video you're going to see suddenly we move up onto the mast, there's a bad signal to noise ratios or signal to interference or noise ratio, and our uplink suffers. The downlink seems to be fine because remember, the downlink does not have limited power. I have limited power transmitting to the uplink. The downlink does not have that same limitation, and the main dilemma in downlinks is normally congestion. It can also be a signal to interference and noise, but more often it is actual congestion on downlinks, just a bit of a practical thing to consider. We are not saying that the Teltonica internal antennas or the antennas that are used internally are bad antennas. Not at all. They're actually quite good antennas. All we're saying is that an external antenna will always win over an internal antenna simply because of the attenuation of the radio signal from the outside having to come through walls, reinforced concrete, etc., etc. So hence the reason why you would be looking at putting an ePoynt-1 omnidirectional antenna on the outside in this instance. You've seen that I've just used the suckers and I've put it on the window outside here, outside of the lab. Thank you for watching. The next one that we're going to do is going to be taking the ePoynt-1, putting it up on a mast, and let's see what the difference is between where it is on the window versus where I'm going to put it on the mast. I'm going to show you that.